Welcome to this episode of Mr. Lehman's Knowledge Explosion. In Lesson 2, we're going to talk about logic and reasoning and the foundations that build that. To start with, you just watched a video on conditional statements. A biconditional statement is a statement that contains the phrase if and only if, and it's the same as writing the conditional statement and the converse at the same time. For example, if I start with a conditional statement that says, if three lines are coplanar, then they lie in the same plane. The converse of that would be, if three lines lie in the same plane, then they are coplanar. The biconditional statement of that is going to take both of those phrases and put it together using the phrase if and only if. So if you ever see that phrase, if and only if, you're actually talking about the conditional statement and the converse rolled into one. So the biconditional would say three lines are coplanar if and only if they lie in the same plane. So it's difficult to decide if a biconditional statement is true or false. In example number 1, it says x equals 3 if and only if, there's the clue that it's biconditional, x squared equals 9. Well, x equals 3 if x squared equals 9, but what about x equaling negative 3? If x is negative 3, then negative 3 squared is still equal to 9. So x doesn't have to be 3. It could be, but it doesn't have to be. So this would be a false statement. And what I want you to understand is a biconditional is only true if both the conditional and the converse are true. Again, a biconditional statement is true if both the conditional and the converse are true. If both statements are not true, then the biconditional statement is false. So let's look at a couple examples down here. For example, number 3. Number 3 says you scored a touchdown if and only if the football crossed the goal line. To decide if this is a true or false statement, we need to rewrite it as the conditional and the converse. So the conditional would be if you score a touchdown, don't mind my abbreviating here, I don't have a lot of room to write. If you score a touchdown, then you cross the goal line. Simple enough. Now to write the converse of that, I switch the hypothesis with the conclusion. Remember, the hypothesis is the part that follows the if, and the conclusion is the part that follows the then. So I'm going to switch those two things around. The converse would be if the ball crosses the goal line, then that's a touchdown. Now, at first glance, this may seem like a very true biconditional statement. If you score a touchdown, then the ball crossed the goal line. That is true. That must happen before you can score a touchdown. However, if the ball crosses the goal line, is it necessarily a touchdown? Does the ball cross the goal line when you kick off? Does the ball cross the goal line when you kick a field goal? Does the ball cross the goal line when you throw an incomplete pass into the stands? Well, yeah, it does, but none of those things are considered touchdowns. So the converse of this statement is actually false. So overall, the biconditional statement is also false. And again, a biconditional statement is only true if both the conditional statement and the converse are true. Now, something that I didn't make very clear in your first video was sometimes you use letters P and Q to represent the hypothesis and conclusion. So the hypothesis is always the P. So if you ever see this phrase, the P is referring to the hypothesis, and the Q is referring to the conclusion. So sometimes you'll see these arrows. P leads to Q, or the hypothesis leads to the conclusion. So the converse would be the conclusion leads to the hypothesis. We switch the order. The inverse always puts in the negation. So if you ever see this mark, not P leads to not Q. That's saying the same thing as the negation of the hypothesis leads to the negation of the conclusion. And then the contrapositive we learned switches that around. So that would be the opposite of the conclusion leads to the opposite of the hypothesis. So if you ever see those markings, understand you're still talking about P is the hypothesis and Q is the conclusion, and we can write them in any order. So that's a nice little review of your converse, inverse, and contrapositive. The main goal of this lesson, though, is to get you thinking about deductive reasoning. We've already talked about inductive reasoning, which uses patterns and examples, and we make conjectures, and then we try and prove them true. Deductive reasoning is different. That uses facts and definitions and postulates to write a logical argument like we tried to do on our last assignment. Deductive reasoning is like Sherlock Holmes saying, well, this person has the fingerprints, their blood is at the crime scene, therefore they were there, they were the only one that was there, so they must be the culprit. That's deductive reasoning. And there are two laws of deductive reasoning. We have the law of detachment, and we have the law of syllogism. And in these laws, you're going to see that idea of P leading to Q. So the law of detachment says this: if P leads to Q is a true conditional statement, and P is true, then so is Q. So let's look at an example of that. In example number 1, it says, if the sun is shining, then it is a beautiful day. The next statement says, the sun is shining. So the hypothesis is true. If the sun is shining, then it's a beautiful day. The sun is shining. So what can we conclude? We can conclude then it's a beautiful day. So this would be a valid use of the law of detachment. Now, the one part you may argue with is, well, I like rainy days and sunny days are not beautiful to me. That's the one part of detachment we have to agree on. If the conditional statement is originally true, then this works. So if your original statement is not true or just opinion, well, then law of detachment doesn't work. Let's look at another example, number 3. This is my sister Cheryl. She becomes a nurse. We told her if she becomes a nurse, she has to take care of my father when he gets old and can't take care of himself. So, if Cheryl becomes a nurse, then she will take care of her father. Cheryl is currently taking care of her father. Can we conclude that Cheryl must have become a nurse? Well, no, that's not how it works. If you write down the hypothesis was if she becomes a nurse, that would lead to the conclusion she'll take care of her father. Is there more than one way that she could have taken care of her father? Sure. Maybe she became a doctor, but she still had to take care of her father. Maybe she became a dentist and she has to take care of her father. Maybe she's unemployed and takes care of her father. It does not matter. The conditional statement said that the hypothesis of becoming a nurse would lead to taking care of her father. We didn't know that she became a nurse, so we can't conclude the opposite. So this would be an invalid use because it doesn't follow in the proper form. The hypothesis leads to the conclusion. A conclusion does not lead backwards to a hypothesis. So please take careful note of that. So that's a couple examples of the law of detachment. The law of syllogism is a little bit trickier. It says if a hypothesis leads me to a conclusion, and then that conclusion leads me to a new conclusion, then the original hypothesis eventually leads me to that final conclusion. So if P leads me to Q and Q leads me to R, then P obviously eventually leads me to R. Let's look at an example of that. In example number 2, it says, if Chris watches a karate movie, then he beats up his little brother. This was what happened to me every time my brother Chris watched a karate movie. He would beat me up, so it was guaranteed. The second statement says, if Chris beats up his little brother, then he gets grounded for a week. Also, rule of my parents' house, always happened. So these are two true conditional statements. So let's see if it follows the correct order of things. If Chris watches a movie, so that's a hypothesis, that will lead to beating up his brother. If he beats up his brother, so that same hypothesis led to that conclusion gets repeated, then he gets grounded for a week. So that's a new conclusion. So P led to Q and Q led to R. So the conclusion should be if Chris watches a karate movie, P, that should lead to getting grounded for a week, R. This is a valid use of syllogism. Many times you'll hear me refer to this as cutting out the middleman. Watching the karate movie will eventually lead directly to getting grounded. Let's look at an example that doesn't work though. In example number 4, I have two if-then statements. That's a clue in that it's going to be syllogism. If Eric plays too much Call of Duty, so there's a hypothesis, then his girlfriend is going to dump him. That's a conclusion. If he plays too much Call of Duty, that's the same hypothesis or the same P, then he will lose his job. That's a different conclusion. So P leads to Q and P leads to R. So can I conclude that if Eric's girlfriend dumps him, Q, that will lead him to losing his job, R? Well, at first glance, you're probably thinking, no, this doesn't make any sense. And you're right. This would be an invalid use of syllogism. If he plays too much Call of Duty, he'll lose his girlfriend. If he plays too much Call of Duty, he'll lose his job. So if he plays too much Call of Duty, he's going to lose his girlfriend and his job. But just because his girlfriend dumps him doesn't mean he's going to lose his job. Maybe he loses his girlfriend because he didn't take her to nice places, or maybe he wasn't a gentleman, or maybe he's a slob. But none of those things are going to affect his job, only his relationship with his girlfriend. So we have to say this is invalid because the hypothesis has to lead to a conclusion. That conclusion leads to a new conclusion, so which means the original hypothesis will lead us all the way to the new conclusion. If it doesn't work like that, it's invalid. See if you can finish the rest of these examples and the examples from Lesson 2 practice from your workbook, and see me if you have any questions. Good luck.